Well, hi there, sports fans. Welcome to another exciting edition of Physics 12. Today we're looking at lesson 5.3, and the main point of today's lesson is looking at vertical circles and how they're different from horizontal circles, which they are. The first thing we're going to look at, though, is we're going to look at curves on a highway, and in this case they're going to be banked as opposed to just being horizontal. And we'll see how that changes things in terms of highway design and on-ramps, off-ramps, that kind of thing, and the curves and how they assist a vehicle in going around a curve. So here's a typical sort of example. So with the banked curve, you can see this is a cross-section of the ground that the car is moving across. It's moving in a circle. Or on a curve. So banking the curve can help keep cars from skidding. In fact, for every banked curve, there is one speed where the entire centripetal force, in other words, toward the center of the circle or toward the center of the curve, the entire centripetal force is supplied by the horizontal component of the normal force, and no friction is actually required. And so this is the reason why they actually bank curves, especially on and off ramps, is that under icy conditions, the vehicle will not require very much friction in order to navigate the curve on an on ramp or an off ramp, provided the vehicle follows the posted speed. So what should the banking angle be for a highway off-ramp of a curve with radius 50 meters and a design speed of 60 kilometers an hour? So most of the on and off ramps that we encounter, they have a posted speed of 60 kilometers an hour. And so we want to know is what banking angle do we need such that the entire centripetal force can be provided by this component of the force right here. And so we'll work through that problem here first. So again, we start with a diagram, of course, where we heard that before. So here's a diagram. Now it is a little bit different from the ramps that we looked at earlier, or the inclined planes. So you'll see that it's a little bit different. We don't talk so much about squeeze and slide. The forces that we talk about are a little bit different here, so you need to follow closely here. There's our angle. And here's a normal force again, which is perpendicular to the surface of the road. Here is the y component of the normal force. That's one of the components that we need to look at. Here's the x component of the normal force, the other component we need to look at. Now notice again, we put the force of gravity on the vehicle straight down, which it should be, but we're not going to worry about squeeze and slide forces right here. This is more what we're concerned about, is the components of the normal force. And indicate the direction of the acceleration. The acceleration needs to be directly toward the center of the circle. So that is indeed the direction for acceleration in this case. So we'll put some numbers on here. The radius of the curve is 50 meters. The speed that we need is 60 kilometers an hour. And so we'll first change that to meters per second. So to change 60 kilometers an hour to meters per second, we multiply by 1,000 meters in a kilometer, and then divide by 3,600 seconds, which is in an hour. All right, and we get 16.7 meters per second. So there's our radius, there's our speed. And let's look at the forces in the y direction here now. So we need balanced forces because there is no acceleration in the y direction, so the forces in the y direction have to be balanced. And so the y component of the normal force then has to equal mg. Now, you need to be a little careful with your geometry here. If this is our angle theta right here, then this also will be our angle theta. So now we can get another expression for Fny, and that's going to be Fn cos theta. So if this angle is theta, then that component will be Fn cos theta. So Fn cos theta has to equal mg, and now we can get an expression for Fn here which equals 9.8 m divided by cos theta. So we do have three unknowns there, but we'll work through this and see where it takes us. So we'll look. There's our expression for normal force from our y direction. Now let's look in the x direction. And now what we've got is we have acceleration in the x direction, and that acceleration is produced by the x component of the normal force, and that has to equal the acceleration in a circle, which is mv squared over r. So there's another expression for Fnx, or that's an expression for Fnx, and now we can work that out as well, because Fnx, this component, has to equal Fn sine theta now. This one will be Fn sine theta. So Fn sine theta has to equal mv squared over r. Now we can get an expression for Fn as well. So Fn is going to equal mv squared over r sine theta. So now we have the two expressions for Fn, and obviously they have to equal each other, so we can just make them equal to each other. And when we do that, we see that we've gone from three unknowns to two unknowns, but this simplifies even further. If you notice, the m's will cancel, and we'll rearrange this equation a little bit. We'll move the 9.8 down there, and we'll move the sine theta up here. So what we get then is, let's move that out of the way a little bit, we get sine theta over cos theta equals v squared over 9.8 r. All right, and now you should recognize this trig identity right here. Let's bring that up a little bit. And there it is here. So sine theta over cos theta is tan theta, and we've gone over that before previously in this course. And that has to equal v squared over 9.8 r, so it'd be 16.7 squared divided by 9.8 times 50. Yes, 50, which is the radius of the curve, 50 meters. All right, so then now we can solve for the angle. Theta has to equal tan to the minus 1. When you work this out, then you will get 0.5669. So we use the inverse tan, and we get an angle of 30 degrees. So this is a really nice example of a banked curve type of a problem, and it's the kind of problem that you will see with this topic. All right, so let's move on then. The other example we're going to look at today is a vertical circle. So now instead of horizontal circles, we're going to look at a problem involving a vertical circle. So this represents, there would be a string attached to the ball from the center of the circle of motion here. And what we're going to do is we're going to look at how the forces differ from the top of the motion to the bottom of the motion. And you can see that if we have a tension force on the ball at the top, the tension force is in the same direction of gravity. At the bottom, however, the tension force is in the opposite direction of gravity. So that's going to change the forces on the ball when it's at the top of the motion as opposed to when it's on the bottom of the motion. So we'll see how that works out now. So compare the tension in the string at the top of the circle with the bottom of the circle if the ball is moving at 4.0 meters per second at each location. So it's moving 4 meters per second here, and it's moving 4 meters per second down there. So let's see what tensions we need in order to keep the ball moving in a circle at both of those locations. So let's first look at the, well, we would do a diagram first, but really there's not much I need to add to this. This is pretty much really all you need on your diagram. We have force of gravity down, and we have the tension force down when it's at the top, and then when the ball's at the bottom, we have a tension force up, and then we have the force of gravity down at that location. Let's put some numbers in now. The speed in both locations is 4.0 meters per second. The mass of the ball is 0.3 kilograms. The radius is 0.72 meters. And at both these locations, we need the sum of the forces has to equal the mass times the acceleration of the ball. All right, so let's look at the top first. Now, Both forces are in the x direction, so both the tension force and the force of gravity are accelerating the ball in a circle. So Ft1 plus mg in this case now equals mv squared over r. So we can just put the numbers in there, and Ft1 plus 0.3 is the mass of the ball times g, 9.8. And then the mv squared over r is 0.3 times 4.0 squared divided by 0.72. And I trust you can do the arithmetic on that. And we'll get the tension force has to be 3.73 newtons at the top of the motion. All right, so let's see how that compares with the bottom. So let's look at the bottom now. When it's at the bottom, we have a tension force up, we have the force of gravity down. We'll call the up direction, we'll call that positive. And so Ft2 minus mg now, okay, at the top it was plus, now it's going to be minus because they're in opposite directions. That now has to equal mv squared over r, and that's going to change our answer quite considerably. So we put the numbers in here, Ft2 minus 0.3 times 9.8, that has to equal 0.3 times 4.0 squared divided by 0.72, and I trust you can do the arithmetic on that. And at the bottom here now, we get a tension force of 9.61 newtons, so quite a bit different than at the top of the motion. And so here's our two different tensions now. And so at the top of the motion, we have a tension force needed of 3.73 newtons. At the bottom, the tension force needs to be 9.61 newtons. And if you think about it, it makes sense, because at the top you've got gravity that helps to accelerate the ball in its circular motion. So you've got gravity assisting the tension force, they're both in the same direction. But at the bottom you've got gravity working against the force of tension. So you'll need to have a greater tension force at the bottom. And anybody who's twirled something around on a string in a vertical type of a motion, you've probably experienced that yourself. You know that the force at the bottom of the motion is going to be a lot more, the tension force is a lot more at the bottom of the motion than it is at the top. And this explains why. So vertical circles, quite a bit different from horizontal circles, and this is the main difference between them. As long as you've, again, your diagram is right, you've got your forces pointed in the right direction, then you should, again, have a lot of success with these kinds of problems.